Welcome in this quick video about different safety measures that are used in electrical networks around houses. A typical household, there will be a connection to the city or the town's electricity net, the grid, via a terminal. This terminal, if we want to mark it, would be this box here in the schematic. The terminal has two things: a main switch, which you can just turn off to shut down all electricity in the house. If you ever go on vacation and through good planning you've eaten all the food in the fridge and the freezer, you could just turn off your terminal and just make sure that you don't use any electricity anymore while you're on vacation. You do have to be careful though. If you use things like electric heating and you go on a winter vacation, you want to make sure that your house is still kept to a minimum temperature, of course. The other thing on the terminal is your kilowatt hour meter, which is number 3 here. This measures the amount of electrical energy you've used throughout the year. Nobody knows exactly how much electricity they will use during a year. So, in order to fix this, you typically pay a deposit. You pay ahead of time for your electricity. And at the end of the year, they will come and check how much electricity you've effectively used. If you have paid more through your deposits than you have used, you will get your money back, of course. However, if you've used more energy than you have paid for so far, you will have to pay extra, of course. And they will adjust your deposit, they will increase it for the next year. Now, after this terminal, you get to part number 4, which is the fuse box. This thing here, installed in most people's garage or basement, whatever it is. There will be several safety features in this fuse box, and it will split up the main network into many different circuits. Circuits can be used, for instance, for outlets in a given room. You can have a circuit for the outlets in your living room, in your bathroom. One or even more in your living room is also an option, because each circuit can only draw so much current before it starts getting overheated. More on which later in this video. You will have a separate circuit for your lighting, etc. And if you use particularly powerful appliances, such as an electric oven, a washing machine, a dishwasher, they will often have their own separate circuit for that, because that will lead to a lot of current. The 3 ways where they will ensure the safety of your electricity, there's 3 ways to do this. Number 1 is a fuse, number 2 is grounding, and number 3 is a ground leakage circuit breaker. We'll tell you what that one is at the very end and note a few things down here. The first one we will discuss is a fuse. Now, as we've seen before, if electricity runs through a wire, that wire will get hot. It's the Joule effect. The equation for that is something we've also studied, and you will notice that current is quadrupled in this case, is to the second, because it's a very important factor in determining how much heat is generated. And heat leads to a potential fire hazard. So you cannot have too much current flowing through a single cable, or your house might burn down. How do they do this? Well, there are 2 types of fuses that they can use: melting fuses and automatic fuses. Melting fuses are no longer in use, and everyone should be using automatic fuses by now. Automatic fuses, they have an electromagnet inside of them, and if too much electricity flows through it, the magnet in it will become too powerful, and that will unhook, that will draw in a switch and open up the circuit this way. Melting fuses are essentially fireproof cases with a built-in weakness, a thin wire in there. Meaning if something is going to melt in your circuit, it will melt in the weakest spot, your melting fuse. These, however, are not used in households anymore. The big disadvantage to them as well was that if they work when they melt, the whole circuit will be broken and you can't fix it anymore. An automatic fuse is one you can switch on again afterwards. However, always check first what might be causing the problem, because there are two major ways where you can cause a problem of too much current. The first one is a short circuit somewhere. Now, a short circuit can happen when the device that you're using is damaged. If the red wire and the blue wire touch, you will create a short circuit. Now let's explain what we mean with red and blue wire. Electric cables consist of 3 different wires. The first one is the live wire. And that one, the live wire, is the one that has the voltage on it. It also has a blue wire. The blue wire is the neutral wire, and that has no voltage on it, or 0 voltage in this case. Under normal circumstances, electricity will flow from the red L wire, can also be brown in some households, from the red wire to the blue wire, and in that way it will close the system. The yellow and green wire is the grounding wire, in this case, quite often given a symbol of grounding as well. This is a safety feature we'll be talking about in a bit. Right? The dangerous part is if your live wire touches the neutral wire inside of your appliance, you will essentially create a short circuit which will not have enough resistance, and current and resistance are inversely proportional, so you'll get way too much current in your circuit. The second major way to cause too much current is by simply overloading it. That's when you hook on too many high power, which is an important point, high power appliances. If you use 100 cell phone chargers, you will not overload your system. Even if it's a quick charger of like 35 amps, which is a lot, you will still not be overloading a traditional outlet circuit. However, if you do the following, you have both a toaster plugged in, which is very high power, a vacuum cleaner, which is very high power, and an iron. I don't know what exactly you would be planning on doing by connecting these 3 in particular, but you will be overloading your system. You will have too much power plugged in. This schematic sort of shows it. You do not have to learn this by heart. There's no need to. But take a simple outlet circuit. It should have an automatic fuse that only allows for 20 amps. Now we can calculate easily how much power this is. Power equals voltage times current. In this case, this circuit operates at 230 volts, like all traditional household circuits do. And if you multiply this by 20 amps, it means that you can easily calculate that you should not connect more than 4,600 watts worth of appliances to it. A previous example, for instance, vacuum cleaners can easily go up to 2,000 watts, so can irons, and if you plug in a toaster on top of that, which will be like 1,000, you will overload your system. You will also notice that some of them, like washing machines and ovens, really allow for a lot of current, but that is because they do require a lot of power. My own personal oven, an electric cooker, is 7,700 watts, so it does require a fuse of more than 40 amps in this case. This is fire hazards. The next big thing is electrocution. You can get an electric shock. Now, an electric shock can be is a connection with a large copper loop to the earth with very little resistance. If you ever come into contact with that current live, that voltage carrying live wire, the electricity will go to the ground, which is 0 volts in this case. If you have a grounding connected to it as well, your electricity has two ways of flowing, via the body or via the current. If the resistance of this grounding is very low, the majority of it will be flowing via the grounding towards the floor. What are these three resistances that they explain here? Well, the total resistance of a human being can vary a lot. It depends on what part of your body is touching the live wire, the path it follows through your body, and the third resistance in series is how much resistance the contact area between your feet and the floor are. Well, traditionally, your feet and the floor. All three of them will add to the resistance of your body, which again should be higher, preferably, than the resistance of grounding. Now, the last one that we use is one we've mentioned here, which is the ground leakage circuit breaker. It is one hell of a long description, but what does it do? Technically, it measures outgoing and incoming current. It should be the same, so these should be equal. If there is a difference, somebody or something is being electrocuted in this case. Now, it is fairly accurate in normal rooms, or if you're talking about normal rooms, for a normal room it would be about, I think, if the difference is greater than 300 millivolts, the current will be turned off. It will all shut down. For a wet room, like a bathroom, it's even more sensitive, and it will shut down if the difference is greater than 30 millivolts. Quite often, your children's room will also be extra protected with just a minute difference of 30 millivolts in order to shut it down. Grounding and ground leakage circuit breakers work in tandem. If a lot of current is escaping via the grounding, let's hope so, right? Instead of through the human body, the ground leakage circuit breaker will detect this and shut everything off. So these two together will hopefully prevent a lethal electric shock. That's it for this chapter, and in fact that's it for the entirety of electricity so far. Our next chapter will be electromagnetism, and I hope to see you then. Bye.